A full table scan occurs when the database engine reads every single page of a table from the storage disk into memory because no suitable index is available. This linear search scales poorly as the row count grows, causing massive latency in large datasets. B-tree indexes reduce search complexity from linear to logarithmic time. Instead of checking every row, the engine traverses a tree structure, following pointers from the root node to specific leaf nodes where the actual data addresses are stored. The cost-based optimizer evaluates multiple execution plans for a single query. It assigns a numerical cost to each plan based on estimated processing cycles and disk operations, choosing the one with the lowest predicted resource consumption. Optimization depends on accurate statistics. The engine maintains histograms showing the distribution of values in columns. If these statistics are stale, the optimizer might choose an inefficient plan because it miscalculates how many rows will be returned. Cardinality estimation predicts the number of rows passing through each operator. Significant gaps between estimated and actual row counts often indicate that the optimizer is blind to data correlations, leading to poor join strategy selection. Nested loop joins are ideal for small inner datasets. The engine takes each row from the outer table and searches for a match in the inner table. Without a supporting index on the inner join key, this operation becomes computationally expensive.
Hash joins handle large, unsorted datasets by building a hash table in memory from the smaller input. It then probes this table with the larger input. If memory is insufficient, the operation spills to the storage disk, drastically slowing performance. Merge joins require both inputs to be sorted on the join keys. The engine reads both inputs simultaneously, matching rows in a single pass. This is often the most efficient join for very large datasets that are already indexed or sorted. Search argumentable predicates, or sargable queries, allow the engine to use indexes effectively. Avoid wrapping columns in functions within the where clause. Applying a function to a column forces the engine to calculate a value for every row, preventing index seeks. Implicit type conversion occurs when comparing different data types, such as a string to an integer. The database must convert the column values for every row to match the constant, which invalidates index usage and triggers a full scan. A covering index contains all the columns requested by a query. This allows the engine to satisfy the request entirely from the index pages, bypassing the need to access the main table data, which reduces total input-output operations. When an index is not covering, the engine performs a key lookup to retrieve missing columns from the table. If the number of lookups is high, the cost may exceed a full table scan, causing the optimizer to abandon the index.
Frequent updates and deletes cause index fragmentation, where data pages are no longer contiguous or have excessive empty space. Fragmented indexes increase the number of read operations required to scan the same amount of logical data. Parameter sniffing happens when the engine creates a plan based on the first parameter value it sees. If that value is not representative of typical data, subsequent executions with different parameters may suffer from a suboptimal cached plan. For queries with highly skewed data distributions, adding a recompile hint forces the engine to generate a new execution plan for every specific set of parameters. This trades CPU time for a more tailored and efficient data access strategy. Sort and join operations that exceed allocated memory spill into the temp database. Because the temp database resides on disk, this creates an input-output bottleneck. Monitor memory grants to ensure large queries have enough workspace to stay in RAM. Parallelism can speed up large scans, but excessive threading causes overhead from coordination and context switching. Configuring the maximum degree of parallelism prevents a single query from consuming all available CPU cores and starving other system processes. High CX packet wait times often indicate skewed data distribution in parallel operations. One thread might be doing significantly more work than others, forcing the rest of the threads to sit idle while waiting for the bottleneck to clear.
Filtered indexes cover only a subset of rows, such as rows where a status is active. These indexes are smaller, faster to update, and more efficient to scan, because they exclude irrelevant data from the index tree entirely. Partitioning divides a large table into smaller, manageable pieces based on a key, like date. The optimizer uses partition pruning to ignore entire sections of the table that do not contain data relevant to the query filters. Use the explain analyze command to view the actual execution plan, rather than the estimated one. Comparing the two reveals where the optimizer made wrong assumptions about row counts or data distribution during the planning phase. Logical reads occur when the engine finds data in the memory buffer cache. Physical reads occur when it must fetch data from the disk. High physical read counts are the primary targets for optimization to reduce query latency. High isolation levels can cause execution plans to stall due to row or page locks. Analyzing lock weights helps distinguish between a slow execution plan and an execution plan that is simply waiting for another transaction to release resources. The query store captures a history of plans and performance metrics. It allows analysts to identify plan regressions, where a query suddenly performs worse because the optimizer switched to a different, less efficient execution strategy over time. Column store indexes store data by column rather than by row. This is highly effective for analytical queries that aggregate large amounts of data, as the engine only reads the specific columns needed for the calculation, ignoring all others. Batch mode processing handles groups of rows together rather than one by one. This reduces the instruction overhead per row and leverages modern CPU features like vectorization, significantly boosting the throughput of heavy analytical workloads. Materialized views store the physical results of a complex query on disk. When the base tables are updated, the view is maintained, allowing subsequent reads to bypass expensive join and aggregation logic during query execution. The optimizer often unrolls subqueries into joins to find a better execution path. However, correlated subqueries can force row-by-row processing. Rewriting these as standard joins or using common table expressions often improves the execution plan structure. The exists clause often outperforms the in clause for semi-joins. Exists stops searching as soon as it finds a single match, whereas in might attempt to evaluate the entire subquery result set before proceeding with the main query logic. Window functions like row number or rank require a stop and sort operation in the execution plan. If the sorting cannot happen in memory, it creates massive disk pressure. Ensure the underlying data is indexed to support the partitioning and ordering clauses. A table spool is a temporary work table used to store intermediate results for reuse later in the query. While spools can save computation, excessive spooling suggests that the execution plan is inefficiently handling large intermediate data volumes. The tipping point is the threshold where the optimizer decides a table scan is cheaper than an index seek followed by lookups. This usually happens when a query retrieves more than a few % of the total rows in a table. Predicate pushdown moves filters as close to the data source as possible. By filtering rows early in the execution plan, the engine reduces the amount of data that must be passed through subsequent joins and transformations. Modern database engines use adaptive query processing to adjust execution plans in real time. If the engine detects a cardinality mismatch during the first few steps of execution, it can switch join types on the fly to prevent performance collapse. Memory grant feedback allows the engine to learn from past executions. If a query was granted too much or too little memory, the optimizer adjusts the grant for the next run, minimizing both resource waste and disk spills. Interleaved execution pauses the query plan for multi-statement table-valued functions to calculate actual row counts. This pause allows the optimizer to make better downstream decisions based on real data rather than blind guesses. When a known good plan is replaced by a bad one, you can force the previous plan using its handle. This provides immediate stability while you investigate the underlying cause of the plan change, such as data drift or updated statistics. The plan cache stores compiled execution plans to save optimization time on subsequent identical queries. Excessive ad hoc queries can bloat the cache, pushing out useful plans and forcing expensive recompilations for frequently executed statements. Anti-joins find rows that do not have a match in another table. Using not exists is generally safer than not in, because not in will return 0 results if any value in the subquery contains a null, often leading to unexpected behavior. Set statistics I/O and statistics time to on to get a raw breakdown of performance. Focus on the elapsed time and logical reads. These metrics are more reliable for comparing plan efficiency than the cost percentages shown in visual execution plans. In some database systems, common table expressions act as optimization fences, meaning they are materialized first. This can prevent the optimizer from pushing filters down into the CTE, leading to massive amounts of unnecessary data being processed. Plan guides allow you to attach query hints to statements that you cannot modify directly in the application code. This is a powerful tool for fixing performance issues in third-party software where the source code is inaccessible.
Blocking is a linear wait for a resource, whereas a deadlock is a circular dependency where two processes wait for each other. Optimized execution plans reduce both by minimizing the time locks are held and the number of pages accessed. System analysts must verify index coverage, update statistics regularly, and look for cardinality mismatches. Solving plan hurdles requires a deep dive into the operators to ensure the engine is not doing unnecessary work due to poor query design. Optimization is an iterative process. Start with the high-impact logical reads, then move to join strategies, and finally fine-tune with hints only if necessary. A well-designed schema is always more robust than a collection of query hints.